Okay, I'd like to take a few minutes and talk about when a function is not differentiable at some given x value, say x equals c. Of course, if our function is f of x, then this would be equivalent to saying that the derivative of f at c does not exist. Now, there are three primary ways in which this can happen. First, f of x might have a discontinuity at x equals c. That will prevent it from being differentiable there. Second, if f of x is continuous at x equals c, then still something could go wrong. For example, if the left and right limiting values of the derivative exist but disagree, then we again have a point of non-differentiability. We have created a corner. And also, we have the potential to create a vertical tangent or a cusp in the graph, both points of non-differentiability, as the corner is. If you look at the left and the right limiting values, again, of the derivative, and you discover that they are both infinite. Okay? Of course, we have a vertical tangent when these guys agree in sign. So, for example, they're both positive infinity, or they're both negative infinity, and we have a cusp when they disagree in sign. So if this is positive and this is negative, or this is negative and this is positive. Okay? So that's what we have to watch out for. But why? What's going on in each one of these cases that forces our function to not be differentiable there? Okay, I want to look at each one of these things in turn in a little bit greater detail so that we understand exactly what's going on. Okay? So first, suppose f of x has a discontinuity at x equals c. Why must f be not differentiable there? Well, this is fairly easy to see intuitively if we look at a graph of f of x, although it does depend a little bit on what kind of discontinuity we have. But let's take a look at a graph that has a gap discontinuity in it. Something like this one, perhaps. Now recall, the definition for the derivative of f is the following, right here, and can be thought of as a limiting slope of a secant line, where this numerator here represents the rise and the denominator represents the run. And the secant line connects the 2 points on the graph at some x plus h value and some x value. Of course, here we're interested in the derivative at c, so let me go ahead and make those replacements for x. Okay, so we have the derivative at c is equal to this limit here. And the secant lines we were talking about connect the point on the graph at c, which is this one right here in this particular case, and at some c plus h, presumably where h is getting fairly close to 0. So, if I let h be positive, that might place c plus h here, and the corresponding point on the graph might be this one, and the corresponding secant might look like this orange line here. Of course, as h gets closer to 0, this point here moves closer towards c. And so rather than having this orange point directly above c plus h, we'll have some point closer into this point associated with c plus h, maybe this one. And then, of course, drawing the corresponding secant, we have this, and then letting h get even closer to 0, which means this point here moves even closer to c, maybe here now, shown in pink. And then looking at the associated secant line, we would have something like this, and then continuing this process in the limit, bringing this infinitesimally close to c. The derivative, of course, is the limiting slopes of these secant lines, which looks like it might be just about horizontal there by the time we get here. So again, as h is positive and we're looking at these points here to the right of c, it looks like my slopes are flying off to not flying off, but approaching maybe 0, maybe something a little bit bigger than 0. However, this limit does allow h to approach 0 from the left as well. What happens in that case? For a negative h value, you should be to the left of c. The corresponding point on the graph might be here. And then the corresponding secant line might be drawn like this green line here. And as h gets closer to 0, this point here would move closer to c, just like before, maybe here now. And the corresponding point on the graph, somewhere around here perhaps, and the secant line, maybe something like that. As I move closer still to c, as h gets closer and closer to 0, maybe I get another point like this one, and the corresponding point on the graph, about here perhaps, and the secant line associated with that, something like this. And again, moving even closer still. Let's make this one really close, and the associated point on the graph, and the associated secant line, this yellow line here. You can see what's happening. As this point gets closer and closer to this guy, as c plus h gets closer and closer to c, as h approaches 0 from the left, the secant lines that I'm seeing are becoming more and more vertical, which means their slopes, right? This is some sort of shallow positive slope. This is a steeper positive slope. This is a steeper still positive slope. So we would expect a fairly large positive number there. This would be a really large positive number, and in the limit we would expect this thing to fly off to infinity on the left. The slopes we see are doing this. So this limit cannot possibly agree. We're seeing two different behaviors on the left and right hand side of 0. One is approaching some reasonable slope on the right, but on the left we have a slope that's approaching infinity. And that by itself would be enough to say technically this limit does not exist. Okay? Of course, this is just a gap discontinuity. There are other types of discontinuities we could have at x equals c. We could have a hole. We could have a vertical asymptote. So can we make a more compelling argument to claim that f cannot be differentiable, that this derivative cannot exist, regardless of what kind of discontinuity we have? And we can indeed do that. Consider the following. If this limit did exist, notice the denominator in the limit as h goes to 0, of course, is going to 0. Okay? But that implies, if this limit exists, what does it imply about the numerator? If the numerator was going to anything besides 0, for example, what if the numerator was going to 5? Then you'd be looking at a fraction where you have the top is getting really close to 5, the bottom is getting very small. Overall, the fraction would be getting very large because you're dividing 5 by a really small thing. That in the limit would be flying off to infinity. The only way this limit exists is if the top also goes to 0. But then you have the limit of this, right, the numerator, equals 0 as h goes to 0. This, of course, is a difference of limits, since it's a limit of a difference. So let's split it up, like so. Now notice, this expression here doesn't even have an h in it. So as h goes to 0, this is constant as far as h is concerned. This whole limiting value should be simply f of c. Of course, this is presuming that f of c existed in the first place. But remember, we said if this whole limit existed, then this would be true and this would be true. And this whole limit can't possibly exist if this guy right here doesn't exist. Okay? So writing that over here, we have this. Now, let's make a clever substitution here. We know h is going to 0. What if we let x be c plus h? So as h goes to 0, doesn't x have to go to c? If that's the case, then we could write the limit as x goes to c instead of this, and then this would be f of x, like so, minus f of c, and that would have to be equal to 0. Okay? Now, simply taking the f of c to the other side, we have this guy right here. Now that should look familiar, doesn't it? This is precisely what we mean when we say f is continuous at c. So let's backtrack through our argument here. We started with the assumption that this limit did exist. And if it did, then this was true, and then this was true, and then this was true, and then this is true. Then f must be continuous at c. So if this limit exists, if the derivative exists, it must be continuous. So if we have a discontinuity, then f prime must fail to exist at that same point. So that's why every single discontinuity a graph of a function has is also a point of non-differentiability. Okay, but what about when, and again this is under the assumption that we are continuous now, the limiting value coming in from the left of the derivative and the limiting value coming in from the right of the derivative both exist, but they disagree. What happens then? Well, this is perhaps even easier to see, especially intuitively, if we consider what's going on in such a graph. Consider the following, where c is right here, and what I want to do is look at the limiting value of the derivative as we approach c, let's say from the left. So we're going to come in from this side, and we're looking at the values of the derivative, in other words, the slopes of the tangent lines, as I approach this c value. So to draw in a sequence of those tangent lines, if we're pretty far away from c initially, our tangent line might be here, something like that perhaps. Notice we have a very slight positive slope. But as we bring this point closer to c, we might see tangent lines like the following, like this green one here. Notice the slope has increased somewhat. As we bring this even closer to c, we might have something like this. Notice our slope has increased just a little bit. And in the limit, as we get really close to c, the tangential slope should be fairly close to this. If I can dot that in there, as the limiting slope coming in from the left. However, as I approach from the right, let's say I start at this point here and look at the tangential slope. Notice we start off steeply almost vertical, but steeply decreasing. As I bring this point in a little bit closer to c, we might get something like this, which is not quite as steep, although still a negative slope. And as I bring it very close to c, say right around here, it shouldn't be hard to see that the limiting slope that we're seeing for the tangent should be pretty close to this. Again, just dotting it in there, because that's the important one. Notice the limiting slopes we saw on the left, the yellow slope, and the limiting slope we saw on the right, this purple slope, certainly disagree. One is positive and one is negative in this case. But any disagreement between these two, between the left and right limits, is going to create what we see here, this abrupt corner in your graph. It doesn't make sense to talk about the slope of the tangent line to this abrupt corner, because there is no single tangent line here. It would make just as much sense to draw this purple line in as the tangent as it would the yellow line as the tangent, or even a horizontal line in this case as a tangent. We don't really have a tangent line at c. And since we don't have a tangential slope there, and the derivative fails to exist. And again, graphically, we have a corner. Okay, well now what about vertical tangents and cusps? What's the problem there? Why does the derivative fail to exist? Well, in these cases, we again have a problem with assigning a single value to the derivative, a single finite value to the derivative in particular. Both of these things are going to see the derivative flying off to some sort of infinite value as we approach our c. So again, just to see that, let's take a look at a couple of pictures. Let's look at this one first. This is a case where we have a cusp at c. Now here's why we have a cusp. Look again at the tangent slopes that one sees as one approaches our c value from the left, and then we'll look at it as we approach c from the right as well. Coming in from the left, here are the tangent slopes we see. Starting with perhaps this one, it's almost horizontal here, very close to 0. Now moving a little closer to c. Notice we have a positive slope here, still not too big of a magnitude, maybe a slope 1 or so. As we move closer to c, now you can see here in this kind of violet color, we have a fairly steep slope. It's also positive. Notice all of these here coming in to c as we get pretty close to c are positive slopes, and they're getting steeper and steeper. So in the limit, our slope is turning vertical, and because it was always positive, we might say that m is flying off to positive infinity on the left. The slopes we're seeing are flying off to positive infinity on the left. Coming in from the right, however, it's a different story. Maybe we start out this far, again, almost a horizontal slope, but as we get closer to c, the tangent slope looks like it's now negative, right? From left to right, it's going down. Okay, but it is getting steeper than it used to be. Moving closer still to c, we see again that the slope is getting very, very steep, but again, left to right, you are falling here. So in the limit, you can think of it as infinitely steep, really the same tangent line that we saw before, but because all of these things were negatively sloped, our slope is approaching negative infinity on the right. So the derivative can't possibly agree. This is kind of a worst case corner. Notice, however, even though the slopes are flying off to the two different infinities here, the problem does not show up as a discontinuity because it is perfectly fine to plug in c and get out some value, some height L here. But calculating a single finite value for the derivative at c certainly is impossible. So we have a point of non-differentiability at c. Now, that's the cusp situation. What about the vertical tangent? Consider this drawing. And again, we're looking at this c value here, which corresponds to this point on the graph. If I look at the tangent slopes coming in from the left as we approach c, notice it's very similar to what we saw here. We would start off with some sort of almost horizontal slope if we started about there, and then it slightly increases, and it slightly increases a little bit more. So we have something like this as a progression. Ultimately, the limiting slope here is vertical. It goes straight up, just like this one did. Again, just dotting it in there, but be careful, I don't mean an asymptote there. But as we come in from the right, we have the reverse of what happened here. Maybe this far away from c, it looks like our slope again is horizontal, like so, but as we move to the left, we see slopes like this one here, and getting even closer to c, we see maybe something like this, and notice these again, as we approach c, are getting steeper and steeper, and they are all positive, just like all of these were positive. In both cases, the tangent slopes we are seeing are flying off to positive infinity. Now that's all fine and good, it's glad to have the agreement there, but that does not mean we can assign a single finite value to the derivative. These things are infinite after all. Okay, so again, we have a point of non-differentiability. The derivative simply does not exist. And again, graphically, we say, in this case, that we have a vertical tangent. And just like in the other case, there's no problem with the continuity of the function here. If I plug in c, I'm getting out some height L here. That's fine. Okay, I don't see the problem until I look at the derivative itself. That's where I don't have a value. And again, let me draw your attention to the distinguishing feature here between a cusp and a vertical tangent. We have a vertical tangent when these limiting slopes of tangent lines are both flying off to infinity and agree in sign. So if these are both positive infinity or if they're both negative infinity, we have a vertical tangent. We have a cusp, on the other hand, when these limiting tangent slopes are flying off to infinity, yes, but they disagree in sign on the left and the right. Whether this is positive and this is negative, or had this been negative and this been positive, we would have a cusp. So again, just to recap, we know a function's not going to be differentiable at a particular x equals c value, that the derivative at c is going to fail to exist if we have a discontinuity at that particular point, or if it is continuous at that point, if we see that the limiting slopes of the tangent lines coming in from the left and the right, the limiting values of the derivative coming in from the left and the right, if they disagree, even though they both exist, then we have a corner. And finally, we see vertical tangents and cusps, also points of non-differentiability, when we look at the left and right limiting values of the derivative and we discover they're both infinite. Again, if these things agree in sign, we're looking at a vertical tangent. If they disagree in sign, we're looking at a cusp. Okay, that's it.